Welcome back, Chemistry Theory. This is the third part for the 16.3 booklet and also the final part for that. So we looked at phase changes there. We'll look at this now, a couple of example questions involving changes in state. So I just pulled these from the textbook. How much heat is required to vaporize 343 grams of liquid ethanol at its boiling point? So if we're looking at this one, we're looking at ethanol going from here to here. So of course this value is different because this one is for water. The enthalpy of vaporization for water is 40.7. Ethanol will be something different. And I gave it to you here. It's plus 38.6 kilojoules per mole. So in order to use that, of course, kilojoules per mole, I'm given grams, so I have to convert from grams to moles first of all, and then I'll be able to use that enthalpy of vaporization value. So of course, to go from grams to moles, I need to know the molar mass. Ethanol, C2H5OH, so there's 2 carbons, 6 hydrogens, and 1 oxygen. That works out to be 46.0 grams per mole. So the first step there is the molar mass conversion. 343 grams multiplied by 1 mole over 46 Gs, because that's how many grams are in 1 mole. So grams cancel, I'm left with moles, and then lastly 1 mole represents 38.6 kilojoules. So here I'm doing the enthalpy of vaporization conversion. So that works out to be 288 kilojoules. Okay, so very similar to what we did with that graphing activity, except we did the gram to mole conversion earlier on. Okay, 8b. How much heat is evolved when 1,255 grams of water condenses to a liquid at 100 degrees C? So evolved means released. So it's exothermic. We treat this as a, and it'll be a negative value because it's exothermic. Okay, so we're going from, let's see, it condenses there. So we're going from, in this case, a vapor to a liquid, just like over here, gas to liquid. Water's value, negative 40.7 kilojoules per mole. But over here in this case, it is water we're working with here. So we use that number, negative 40.7 kilojoules per mole. So we're going from grams to moles to kilojoules again. So again, find a molar mass of water, 18 grams per mole. And so there we have it there. We have to convert it into moles first of all. So multiply by 1 over 18 Gs. The Gs cancel. I'm left with moles. And then over here, negative 40.7 kilojoules is released for every 1 mole. So for the number of moles I have, it works out to be that. Negative 2,838 kilojoules. The negative, of course, means released or exothermic, as was suggested in the question. Releasing heat when going from a vapor back to a liquid. How much heat is liberated by the combustion of 206 grams of hydrogen? And if you recall, hydrogen is a diatomic element, so it's actually H2. And the enthalpy of combustion here, so this isn't a change in state, it's a chemical reaction. We're combusting hydrogen here. And of course that involves the release of heat, so it's exothermic or negative H. So again, grams to moles to kilojoules. The molar mass of hydrogen is actually 2 hydrogens, so 2.0 grams for 1 mole. So we have the molar mass conversion, and then from there multiplied by the enthalpy of combustion, we get negative 29,500 kilojoules. Okay. Last one. Now this last question I changed it a little bit. Yeah, I wanted to change it to 4.5 kilojoules just to make the number different than over here, because this question usually causes some issues otherwise. A sample of ammonia liberates 4.5 kilojoules of heat as it becomes a solid. So we're going from liquid to solid, so it's enthalpy of solidification. What is the mass of the sample? So this question is exactly opposite. We're going from heat to moles to grams this time. So we know how much heat is involved, and it's liberates. That means releases, so it's exothermic. so it's technically negative 4.50 kilojoules. And of course, to go from heat to moles, we know this, the enthalpy of solidification. Negative 5.66 kilojoules are released for every 1 mole. And notice here that the negatives will cancel. Makes sense because we can't have negative grams in the long run. And then lastly, going from moles to grams, the molar mass of ammonia, nitrogen, 3 hydrogens, 17.0 grams per mole. So that works out to be 13.5 Gs. Negatives cancel. Everything cancels out perfectly here. So of course, looking at these energies, of course, in our everyday, we eat food items, etc., to get this energy because our bodies are constantly burning energy and we have to replace that. Okay, finally the vocab. Now I think we defined these ones before, endo and exothermic, but just to kind of go through that again. Heat going from surroundings to system is endothermic. Heat moving from system to surroundings or being released are exothermic reactions. Thermochemical equation, it's a balanced equation that has heat as a term right in the equation. So one that we looked at earlier, the rusting of iron, involves the release of heat. So I could write it as delta H equals negative 1625 just off to the side. Or I could include it in the reaction itself, but it would have to be on the product side. Enthalpy of combustion, the enthalpy change for the complete burning of 1 mole of whatever substance it is I'm talking about. So for example, enthalpy of combustion of sugar, 5,644 kilojoules per mole. And of course the negative implies that it's exothermic, heat's released. To vaporize, molar enthalpy of vaporization, the enthalpy change when 1 mole of substance goes from the liquid to the gas state. So for example, enthalpy of vaporization of ethanol requires the absorption of 38.6 kilojoules per mole. And similarly here, so they're all similar except the change in state is different. Fusion, going from solid to liquid. So the enthalpy change for, in the layman's terms there, melting 1 mole of solid into a liquid. And we can look at ethanol's enthalpy of fusion value there, 4.94 kilojoules per mole. Okay, so there you have it. That's booklet 6.3.